Welcome to my YouTube channel. So today I will discuss some theorem example of row space. So first theory is row equivalent matrices have the same row space. So we have discussed what is row space, column space in the previous lecture. If you didn't watch, first watch that video. So row space means if A has R m rows, that is R1, R2 dot Rm, then these rows are belongs to K n as A is a m cross n matrix, so it has n columns. So each rows can be considered as a vector in Kn. Then these m rows will span a space which is called row space. And in similarly, if we discuss with respect to column, then the columns, m columns of the matrix column vector that contains m elements. So each column belongs to km. So co1 dot cn will span a space which is called column space. So the row equivalent matrices have the same row space. And the second theorem, it is very important theorem. Suppose AB are two canonical matrices, row canonical matrices. So you see that row reduced or canonical form, echelon form, and row reduced echelon form. In row reduced echelon form, each column which contains pivotal element, other than pivotal element, all entries in that column will be zero. In row echelon form, row reduced echelon form, and each pivotal element is 1. So this is the difference between echelon form and row reduced form. Echelon form, so we have discussed, you can watch that video. So if these two matrices are row canonical matrices, that is row reduced echelon form, okay, then A and B have the same row space if and only if they have the same non-zero rows. So if you are given two matrices A and B, so let first reduce them to canonical form. Canonical form means row reduced echelon form. Okay, first make them row reduced echelon form. Similarly, write B in row reduced echelon form. So if this is A dash and this is B dash, so now we see A dash and B dash. If these two row canonical matrices have the same non-zero rows, so if it has a rows R1 which is similar to this row in B dash, then we say this matrix are same row space. Then AB have same row space. So now we discuss one example which we will solve using this theory. Let us take that example. This is the example. Consider the following two sets of vectors in R4. One contains u1, u2, u3, so which are given, and the other set contains two elements w1, w2, which are given. So u equal to span of these vectors u1, u2, u3, and w is a span of this vector u2, and w2, w1, w2. So we have to show these two subspace or space are equal. So for that, first we make a matrix which contains u1, u2, u3 as row, -7, and other matrix B by w1, w2 as row. If we can show that A and B's row canonical form have the same number of non-zero rows, same non-zero rows. So if we can find canonical form of these two matrices, and we will check the rows. If the canonical form have same rows, then we say A and B will have same row space. That is, this row will span a space, and this row will span a space, and these two space will be equal. That is, U and W will be equal. So we find this canonical form. So let us find. So first, this is a pivotal element, so we have to make this is 0. So we simply take R2 dash. So we will change R2 as R2 minus 2R1. So if you apply this operation R2 minus 2 R1, and similarly for R3, so R3 new R3 become R3 minus 3 R1. So then the matrix will be look like, so first row will be unchanged, 1 2 minus 1 3, second row this will 0, third row this will 0, so this will be 0 0, 3 minus 8, and third row will be 0 0, 6 minus 16. So this row are same, so this will be 1 2 minus 1 3 0 0 3 minus 8, so this is same. So if we apply R3 dash, R3 minus 2 R2, so this will also 0, so therefore we divide by R2 by 3, so this will be 1, and this will be by 3, so therefore we have to make this is 0, so we apply R1, that is R1 dash R1 plus R2, so this will 1 2 0, and this will be 3 9, that is 1 by 3, and this will be 0 0 1 minus 8 by 3. So this is the canonical form of the matrix A. Okay. Similarly, we find canonical form for the matrix B. So similarly, if we apply R2 minus 2 R1, so therefore we will get 1 2 minus 4 11, and this will be 0 0. So R2 minus 2 R1, so this will be 8, so this will be plus 3, and this will be 14 minus 22, so this will be 8, 22 14, so this will be minus 8. Okay, so this will be minus 8 if we apply this, so this will become this, and therefore again we divided R3 by 3, so this will 1, and this will by 3, and now we apply this, we have to 0, so R1 dash will be R1 plus 4 into R2, so therefore this will be 1 2 minus 4 will be 0, so this R1 11 minus 4 into this 32 by 3, so 33 minus 33 minus 32, so this into 1 by 3, and this will be 0 0 1 minus 8 by 3. So now from A, the canonical form we get this, whose row is 1 2 0 1 3 0 0 1 minus, so 2 non-zero rows, and for B we find canonical form which is exactly same as this, so it has also the 2 non-zero rows which is similar to this. So the matrix A and B, the canonical form of this matrix have the same non-zero rows, therefore we can conclude that these have the same row space, so this will span U and this B will span W, so therefore from this we can conclude that U equal to W. Okay, this is very important problem for your upcoming examination. Now we discuss a very important thing, that is linear dependence and linear independence. So we say the vectors v1 v2 dot vn of a vector space V is linearly dependent if there exist scalars a1 a2 dot am not all 0 such that a1 v1 plus a2 v2 plus dot am vm equal to 0. So these m vectors of a vector space V is said to be linearly dependent if there exist scalars a1 a2 am. This is very important, not all 0 such that we can write this, so otherwise it will be linearly independent. Okay, so you can say in other words, so x1 v1 plus x2 v2 plus dot xm vm equal to 0. If this equation has a non-zero solution, then we call this vector is linearly dependent. Non-zero solutions means x1 x2 dot xn can be found in such a way that not all xi are 0, so there be at least one xj which is not equal to 0. Otherwise we say the vectors this linearly independent if there exist scalars such that this equal to 0 imply all ai equal to 0. Okay, so these vectors is said to be linearly independent if there exist scalars such that this implies all ai 0. So if this equation has only a solution, that is trivial solution, 0 0 solution, then we say this v1 v2 vm is linearly independent. So this is very important. With this concept we will solve many questions which we will discuss later. Now discuss some remark on linear dependence or independence. So first, remark 1, one vector is 0 of this v1 v2 dot dot vm, then this set is linearly dependent. How? So let v1 equal to 0. So therefore we a1 v1 plus a2 v2 plus dot dot plus am vm equal to 0 can be represented as non-zero, that is 1 into v1 baki 0 into v2 0 into v3 plus dot dot plus 0 into vm equal to 0. So there exists one scalar a1 which is not equal to 0. So by definition of linearly dependence we say this will be linearly dependent. So whenever a set of vectors contains 0 vectors, then the set will be linearly dependent. ठीक है. And remark 2, a vector, a single vector say v is always linearly independent because a into v equal to 0 and v not equal to 0 implies that a equal to 0. So we write in the linear combination form of this vector and we get the solution, only the 0 solution whenever the vector is non-zero. So this is linearly independent. And the remark 3, any two vectors are equal or one is multiple of another, then v1 v2 vm is linearly dependent. So if we say v1 v2 dot dot vm and we say v2 equal to k into v1, then a1 v1 plus dot dot a2 v2 plus dot dot m vm equal to 0 can be expressed as, so a1 v1 plus can be written as v2 as k v1. So therefore we get non-zero solutions of the system this. So here from here we get a1 and a2 non-zero elements. Okay, so non-zero solution. Or any two vectors, remark 4, any two vectors v1 and v2 called linearly dependent if one is a multiple of others. Okay, so then we call linearly dependent. Remark 5, if a set u1 u2 dot dot un is linearly independent and s is a subset of this li, then this s will also be linearly independent. Similarly, if s contains a linearly dependent subset, then s is also linearly dependent. And also if u1 u2 dot dot um is linearly independent, then any rearrangement. So if you write m here u2 u1 but number of elements same as here, then this also rearrangement of a linear independent set also linearly independent. So these are the important remarks. So for today that's it. So if you like it, please subscribe my channel and share with your friends. I will discuss more things in this chapter. So keep learning, keep watching. Thank you very much.